Hello everyone, I'm Jeff Damont. In this video, I'm going to talk about my favorite big number, how I found it, and why I like it. This is one of a group of videos where people were asked to give their favorite number bigger than 1,000,000. You can find more of these videos under the hashtag #MegaFaveNumbers. Now I'm not a mathematician, but I use math to be a better juggler. For me, juggling is a fun way to explore physics and science. It also makes the math of permutations and combinations more tangible. I do a juggling routine with boxes. Basically, you release 3 boxes in the air, rearrange them, then catch them before they hit the floor. Lots of people had done this before me, but my goal when I started was to come up with as many new tricks as I could find. So instead of figuring out tricks one by one, I decided to use math to figure out all of the possible tricks, and then just pick out the ones that I liked best. The question is, from this starting position, how many different ways can you rearrange the boxes? I'll start with the basics before getting to the big numbers. If you already know the basics, you can watch me do tricks in the corner. So from this starting position, you can turn any of the 3 boxes upside down. You have 3 options for turning 1 box and 3 options for turning 2 boxes. You can turn all 3, and you have the option of turning none at all. The number of finished orientations is 2, up or down, and the number of boxes is 3. That makes 8 different ending positions by just turning or not turning boxes. Each box that turns can go clockwise or counterclockwise. So the combinations where 1 box is turned is multiplied by 2, the combinations where 2 boxes are turned are multiplied by 4, and the combination where all 3 boxes are turned is multiplied by 8. A better way to look at it is that for each of the 3 boxes there are 3 options, going clockwise, counterclockwise, or not at all. And 3 rotations to the power of 3 boxes is 27. You can also turn the boxes on different axes. We've been using the shortest axis, but there's also the longest axis and the less stable middle axis. Both directions on all 3 axes, plus the option not to turn, gives each box 7 rotation options. I wouldn't recommend trying to turn boxes on different axes during the same trick, but it is mathematically possible. There are 79 possible tricks where all of the boxes only turn on the same axis, and 343 potential tricks if they can turn on any of the 3 axes. And we haven't even started to switch their places yet. Rearranging the boxes takes a different kind of math. With 2 boxes in a line, there are only 2 possibilities. Add a 3rd box and it can go into 3 possible positions in relation to the first 2, so there are 6 different possible rearrangements, or permutations, of 3 boxes in a line. For all 6 of these permutations, you can put a 4th box into any of these 4 positions for 24 different permutations. Multiply that by 5 to add a 5th box for 120 permutations, and so on. But for now, let's just keep it at 3 boxes. From this starting position, you can finish with the boxes rearranged in any of these 6 positions. You can rearrange the boxes the easy way or the hard way. For example, to switch the 2nd and 3rd box, you can reach over with your right hand, grab box 2, carry it under box 3, and bring the boxes together. Or you can grab box 2, carry it over box 3, and bring the boxes together. Or you can let go with both hands, reach over and grab box 1 with your right hand, carry it around 2 and 3, pass box 1 to your left hand, then grab box 2 with your right, carry it under box 3, and bring the boxes together again. Of course, for that, you have to be fast because your boxes are accelerating towards the floor at 9.8 meters per second squared the whole time. So each time you end with the boxes in the same position compared to your starting position, but they're all different tricks. Next, you can rotate any combination of boxes in any direction as you rearrange their positions. Just multiply the 6 arrangement permutations by the 27 basic rotation combinations for 162 basic tricks. Or 2058 if you could rotate boxes in either direction along any axis as you rearrange them. There's actually 8 basic positions where you can start or catch a trick, and each of those have different options for hand positions. The number of possible tricks gets bigger as you rearrange the boxes starting in one position and ending in another. Once you find your favorite tricks, then there's the number of different orders that you can rearrange them into a routine. This is something that kept me very busy when I was younger. Arranging 10 boxes in a row has over 3 million permutations. You get that by multiplying all of the whole numbers between 10 and 1, otherwise known as 10 factorial, which is written as 10 with an exclamation point. Here I have 5 white and 5 red boxes, and if I switched any boxes with the same color, it would still look the same. So how many different patterns of red and white could I make? You find that by dividing 10 factorial for all 10 boxes by 5 factorial for the red boxes times 5 factorial for the white. You can cancel out 5 factorial from the top and bottom to make it simpler. The answer is 252 different patterns of red and white. You can get some really big numbers with playing cards. When you shuffle a 52 card deck, there are 52 factorial different possible outcomes. That's about 8.065 times 10 to the power of 67. In other words, 8 with 67 digits after it. The first game project I did was to redesign a deck of playing cards replacing the standard suits with a 5-weapon version of rock, paper, scissors. All 5 suits have 13 ranks from ace through king, plus a joker, so the whole deck has 70 cards. And that's why 70 factorial is special to me and is my favorite big number. My phone calculator tells me this is about 1.19 times 10 to the 100. And if I did my arithmetic right, it comes out to this number. But I was curious, just how big is that number, and what can you compare it to? Let's go back to when we had 3 boxes, and each box could be turned one of 2 ways on 3 axes or not at all, for 7 possibilities. All 3 boxes can be represented by a 7. Then you multiply them together for 343 ways to rotate the boxes without changing their positions. If you had 5 boxes, the number of combinations is 7 to the power of 5, or 16,807. Now replace those 5 boxes with 5 Rubik's Cubes. Instead of 7 possibilities, now there is over 4 times 10 to the power of 19. Multiply all the permutations of a Rubik's Cube by itself 5 times. The total number of cube permutations to the power of 5 is still not as big as 70 factorial. Here's another way to look at it. The astrophysicist Arthur Eddington estimated that there were 10 to the 80 protons in the observable universe. If every one of those protons shuffled a deck of 70 cards once every second starting the Big Bang, they would not have reached 1% of all possible permutations yet. So it's pretty safe to say that you will never play the same game of solitaire twice. So 70 factorial is a huge number with universal proportions that can all be represented by a deck of cards that fits in your pocket. Before I finish, I do want to give a shout out to Claude Shannon, who figured out how many different chess games you could play within 40 moves. Shannon's number is about 10 to the 120, and that makes my number look tiny by comparison. But with this number, he was able to show it would be impractical to write a computer program to play chess that just remembered every possible move for every possible game. Most mathematicians will know Claude Shannon for the work he did with early computers as the father of information theory. But I will always know him as the guy who built amazing juggling machines. I'm looking forward to seeing all the other videos people made about big numbers, and I hope you check them out too. And then you can check out my channel for more videos about card games. Thanks for watching and keep having fun.